Hello, this is our second lecture for Elementary of Statistics, and we are going to discuss in this lecture organizing data. This is the same statistical circle that we did discuss before in our first lecture, and we would like today to discuss one step of the data, which is step number 2, organizing data. You remember we said the statistical science is composed of 5 steps: collect, organize, summarize, analyze data, and also draw conclusion. Today's lecture is focusing on organizing data. But before talking about how to organize our data, we will talk about another topic which is needed to go ahead and talk about organizing data. So that topic is variables types. For variables, we do have 2 types. The first one is qualitative type, which is I can have qualitative variables versus quantitative variables. Qualitatives are those variables who are having values as categories or non-numeric in general, and the difference between each value and the other is just it's a distinct class. So a different category, different possible value for a specific qualitative variable is different from another value just because it is a different class. Like, for example, hair color or eye color. The differences between the possible values for each one of these variables is just the difference in color. For eyes, green versus blue versus maybe black or brown. For hair, black, yellow, red, and so on. And other types of that variable could be also types of car, Toyota, Ford, Honda, and so on. A marital status is also a qualitative variable which is having categorical values as divorced, widowed, married, single, and so on. Religion as well, and types of fund. All of these variables are having its values as categories, and the difference between these categories is just a distinct class. On the other hand, for quantitative variables, these variables are either measured or counted or even calculated via a formula. So any variable which is quantitative is gonna come either because it is defined to be the count for a specific variable, or it is calculated or measured somehow. And because of that quantitative variables are divided further into 2 other types. The discrete, which is that variable that is defined upon counting, like number of cars, number of siblings in my family or in the household in general, any household, and also number of accidents. All of these variables are discrete just because the value itself is nothing but a count. On the other hand, the second type of the quantitative variable is what is known by continuous. In a continuous variable, we are assumed that between any 2 given numbers, I will have an infinite number of other values in between. Like if my variable was age and I have 2 age values, 20 and 21, by assumption, I do have as many values as I have between the number 20 and 21 as possible values for that variable age. So infinite number between any 2 specific values are assumed for such variable, any continuous variable, and that variable is usually measured either by calculating it via a specific formula or measuring it using a specific device. Examples for that one is for continuous variable is weight, income, salary, area as a continuous variable that depends on measuring as well or calculated. And for these types of variables, quantitative and qualitative, we do have levels of measurement. So I do have 4 levels of measurements. The first one is nominal versus ordinal, and these nominal versus ordinal, these are the suitable levels of measurements for a qualitative variable. What is the difference between these two if after all they are suitable for qualitative variable? Well, for nominal we are assuming that values which are measured on the nominal scale, you cannot arrange its values. So no order or ranking can be imposed on any data or values for a quantitative variable. Qualitative variable, in this case, this variable is measured on the nominal scale. If, however, there is some order, or you can order the values or the data for a specific qualitative variable, this means this variable is measured on the ordinal scale. So if the values of a specific qualitative variable can be ordered or ranked, then it is measured on the ordinal scale or levels of measurement. Examples for nominal scale qualitative variable is eye color again, hair color, religious affiliation, political affiliation, types of the cars, Honda versus Toyota versus Ford. All of these are just measured on the nominal scale because we cannot rank their values. However, for the ordinal case or ordinal qualitative variables, I can order the values themselves. Like if we were asking someone about how much he or she is satisfied or dissatisfied with a specific service. So I can have options like highly satisfied, just satisfied, neutral, dissatisfied, and strongly or highly dissatisfied. These are measured on an ordinal scale because obviously highly satisfied is higher than the only satisfied response. However, the difference between highly satisfied and satisfied only as a response for that variable ranking for a specific surface is not known. So you cannot really measure it to know exactly what is the difference between these two answers, highly satisfied and satisfied, or these two. So differences between any two levels of that ordinal variable is unknown. Another example could be student classification, freshman, sophomore, junior, and senior. These are distinct and we can rank them as you see here. However, the difference between that one and that one, that response and that response, or that value and that value for that student classification variable is not known or does not exist. So for the quantitative variables, we do have two other levels for measurement or scales to measure them. The first one is interval and the second one is ratio. So quantitative variables are either measured on the interval scale or the ratio scale. What is the difference between these two? For the interval scale, I can rank my data for that quantitative variable. Obviously, any quantitative variable could be ranked because these are numbers after all. So upon that, or after saying that, we can rank them, but it would be measured on the interval scale if there is a precise difference between the units could be measured. and this is like what, like for example, temperature. When I say the temperature today is 90 and yesterday it was 80, so exactly I know that there is exactly a difference between 90 and 80 of exact 10 points. However, interval scale or variables that are measured on the interval scale do not have a true zero. So, or in other words, the zero in that scale does not have any meaning. And a good example for that is again the temperature. If I'm saying today's temperature is 0, this does not mean at all that there is no temperature. Just this is a value that we said it will represent 0 in terms of the temperature, but it's not a true 0. This is similar to the IQ test scores. A 0 score there does not mean that there is no IQ at all. It just means this is the point that everybody agreed to have a 0 on it, but it's not a true 0 like the phenomenon vanished. This is to the opposite of the ratio scale, which is our last level of measurement. Here I can order, obviously, because it's for quantitative variables. I can measure the exact difference between any two values. And also the 0 is meaningful. So because the 0 is meaningful, I can calculate ratios, and because of that we call it ratio. So here we do have a true 0. Like if, for example, your salary don't work and your salary is 0, this is a true 0. You don't have anything at your hand at the end of the month. So let we head to our main topic, which is organizing data. For organizing data, when are we able to begin organizing our data? Obviously, after we did collect it. So assume we did collect the data somehow, either from a sample or from a population, and we need now to organize that data set or display it somehow. So organizing it, or displaying it, we mean actually either to create what is known by a frequency distribution or to have some graphs. Frequency distribution is just a tabular form that I can use to represent or put my data in an organizing my data in a table, where I'm gonna take each value, each class of my variable, I'm gonna put it in a line or in a row in my table and just write beside it how many times did that class appear in my data. And this depends actually to know the frequency and the classes themselves, the non-overlapping classes, again depends on the type of the variable. If my type of my variable was qualitative variable, then this is an easy task for me to create a frequency table or frequency distribution, because all what I need is just to list all the different values of my qualitative variable in that table and count how many times did each class appear. Like if my variable was blood type is a qualitative variable, and it is not only that, it is measured on the nominal scale. There is no order among the different values of my blood type variable, AB and O and AB. If I do have 25 observation or people in my sample, and for each one I did read or I did check or test what is the blood type for each one of those, I will just write in my table how many times among these 25 people I did have blood type A, how many times did I have B, and so on. This is a frequency distribution for exactly how many people. Counting all of these, adding these up, all the frequency will give me 25, which means I began my data with 25 people. If I had quantitative variable, the table is similar, but not exactly. So let me dig into that. For discrete random variable or discrete variables, it is the same like qualitative variable. I will see how many different discrete values for my discrete random do I have. Here for my discrete variable do I have. Here I have a number of pets as my variable, and inside the household I do have either 0, 1, 2, and 3 among my 40 household. Okay, so for each different class, each different value of my variable, discrete variable, I do have to count how many times did it appear in my 40 household. That one, 0 appeared 10, 1 appeared 15. I had 10 households with 2 pets inside it and only 5 with 3. If my variable was, on the other hand, a continuous random variable, then I cannot do the same principle. Like for each value, I will reserve a whole class or a whole row in my table. No, this would be too much. What I'm gonna do is I'm gonna group some of the values inside an interval of values, which we are gonna call class. Because of that, we had here classes in general. Could be one number for discrete random variable, could be a category for qualitative variable, and for continuous it would be group of values. As I do have here age group, which is my random variable is age, and this is a continuous variable. So I have here from 20 to less than 30, all the ages from 20 to less than 30 are in one row, in one class. And again, I am gonna just apply the same principle of calculating the frequencies, or rather counting the frequencies. It is 10 among my 40 people here. 10 of my people are having age between, or in this class, between 20 till less than 30, 15 from 30 till less than 40, and so on. So these are the different tables that you could see or you could use to organize your qualitative variable, quantitative with its two types, discrete and continuous. Because of that fact here for the continuous variables, we needed to group some values together in one class. Sometimes also that frequency table for continuous variable are called grouped frequency distribution, just to emphasize the fact that I do have here groups of numbers together in one class. Now this is to organize it in a tabular form. There are many issues we did not discuss here specifically for grouped frequency distribution, like how to choose how many values do I have in each class. This is beyond our lecture. However, there are some resources out there. If you need it, just check for how to create the classes inside grouped frequency distribution or for continuous variables in general. Now let's move to our second way to organize my data. Well, graphs. I will have, or I can use graphs to represent my data instead of using frequency distributions or table. This is just like a visual summary to put the information of my sample in a nicer way and more compact way compared to that table. So we have here, again, these graphs will depend on the type of your variable. For qualitative variable, we have two types that are mainly used: bar chart and pie chart. There are some others, but we're gonna focus on that only. And also for quantitative variables, we have some other different graphs: stem and leaf if your data set is small, dot plot again if your data set is small, like the items you are having or the sample size is small, histogram, ogive, time series, and later also we will talk about box plot. Not in today's lecture, because box plots needs to know some other measures that we did not cover in this lecture. So later we are gonna cover that also in its practical position of the topics. Okay. So let we begin with bar chart. What is a bar chart? A bar chart, this is a graph where you are gonna represent each class in your table by a bar, and it is again for only qualitative variables or categorical variables. So each class in your table, in our previous example we had, or table that we have seen on our previous slide, it was blood type. So I'm gonna represent blood type 5 as a bar, blood type B as a bar, and so on. And the height of this bar is exactly equal to the frequency, or you could also use the relative frequency, which is the frequency of each class over the total number of the items in your sample. And these bars could be graphed either horizontal or vertical. So I have here a table which is a new one. We have only 20 students in a class, and for those 20 we ask each one whether he or she is freshman, sophomore, junior, and senior, what is the classification of each one. And I can use either a vertical bar chart or a horizontal bar chart to represent it. Here I'm gonna use, let me begin with a horizontal one. So for a horizontal one, I'm gonna represent each class by a bar which is horizontal like that. Okay, so freshman, here is my freshman, and that bar is exactly of height 5. Why? Because I'm using the frequency. I could again use frequency or relative frequency, but in this graph, since I'm using the 5, so this is frequency. Okay, and each other class is represented as well using a bar of the same height as its frequency. I could also use vertical bars, so these bars would be in the other direction, vertical. Okay, and I could use the frequency with it, or I could use relative frequency. It's up to you actually. So if I am gonna use the relative frequency, I will need to calculate it. Again, it's how many frequency over the total. So the total of those frequencies is 20, because we begin with 20 students. So 5 over 20, this is my 1/4. 10 over 20, half, and so on. These should add up to 1. Okay. And now I'm gonna use that as my y-axis, and I am gonna represent the bars in a vertical way. So bar charts are either vertical bars or horizontal ones. You can use the frequency or the relative frequency. From that graph, I can just spot what is the highest frequency, what is the class that is having the highest frequency. Here it is sophomore, 50% if I am looking at the relative frequency. And here also the same information is revealed, but in terms of frequency. My second graph for qualitative variables is the pie chart. Here the idea is different. The pie chart is used to represent relative frequency. So if you are interested in the relative frequency only and not the frequency itself, not the real number, just the relative frequencies, the percentages, so go, and your variable was a qualitative variable, you can use the pie chart. The idea here is to divide the pie into portions. Each portion is connected to each class in your table. How? Using a formula which is saying the angle of this portion is exactly equal to 360, because we do have 360 degrees in the pie. the total number of degrees for the angles is 360. So multiply that by the relative frequency of each class. You will be able to know what is the angle of each portion that will be related to which class. So if this is the case, let me go back to our previous example. And here is the relative frequencies we have seen before. I'm gonna use that column to calculate the angle for each portion. If I did that, you can get it from Excel very easily. You will end up with that graph. So that 50%, this is the class for sophomore. That angle, as you see here, is 180. How did we do that? It's the 50% times 360 will give you 180, exactly that angle. And so on. So let me move to our second type of plots that are suitable for quantitative variables. The first one is a dot plot. In a dot plot, you will represent each value in your data by a dot on above the x-axis. And again, this is suitable, this plot is suitable for small data sets, so like 30 or 40 observations only, maybe 30 only. This plot is really good to determine whether your data is having outliers or not. What is outliers? Outliers by definition is that value among your data values that is either too small or too high compared to the mean bulk of your data values. So extremely high or extremely low data values. The main positive points for the dot plot is that it will allow you to keep track with your data, the raw data values themselves. So it's not like you're gonna forget about the raw data, the values of each data point in your data set. It will allow you to keep track of those values because you don't group your values obviously in any groups. So also that graph will allow you to talk about the shape and to spot any outlier. Let me have an example. We do have here 20 days, 20 points or 20 data points that represent the number of cardiograms performed over 20 days in a specific testing center. These are our data points, 20 points, and we would like to represent it using, since these are 20, I can use dot plot to represent it. Instead of looking that file or those lines for my data, I can just plot it using my dot plot. So my x-axis, I will check what is the smallest value and the greatest value among my data. Here I can spot the two. This is the smallest value, and the largest one would be 57. So I will put here on my data line values from 2 to 57, and I can pick a scale here, like each 1 centimeter. Suppose this is 1 centimeter, okay, and this is another 1 centimeter. So each 1 centimeter could be represented by 10 units. How about that? So 0, 10, 20, and so on. Just pick a useful unit of measurements or for your x-axis scale, and after that you are gonna just put or represent each value as a dot on that graph, because it's a dot plot after all. So the 25, here is 20, here is 30, here is the 25, so my first point should appear here, and my second point is just above the 30, and 20, and 32 and so on. I can do all of these values. If you do have a value that is repeated many times, you are gonna just put it on top of the other. Like here from my completed graph, I do have 32 appeared 4 times because I do have here 4 points on top of each other. Add the 32. And the second one, which is repeated more than one, was 43, I believe. This is our 43 because this is 40. This is 45, so this is 44. Here is 144, and here is the second 44. And these are all of our dots, except for the 2 because 2 is not appeared. Let me just, yeah, here is my 2. Now looking at that graph, I can say I do have 32 repeated 4 times, 44 2 times, so the most frequent value was 32. I can say that that point, the 2, is actually an outlier because it is separated from the main bulk of my data. I could say, well, the data are centered actually here in the middle between 30 and maybe 35. Okay, most of the data are here. Okay, the second graph for small data set and quantitative, of course, is stem and leaf. In the stem and leaf graph, we are gonna do something else. We are not gonna represent each value as a dot on the above the x-axis. However, we are gonna divide each value into 2 parts: the most left part of the number and the right part, usually the unit versus the other tens and maybe 100s and so on. So, and we are gonna call the most, this is the simple version of the stem and leaf plot. We are gonna call part of the numbers that we did split into 2, the most left part we are gonna call it stem, and the right part of my number we are gonna call it leaf. So in this example, this is a stem and leaf plot. The stems are here, these are my stems, and these are the leaves. For each stem you will have one or even nothing at all, okay, either one or nothing. If it is nothing, then you are gonna drop that stem if it was in the tails here or here. But in between, if you did have here a number like 4 was having nothing here, you are to leave it as it is with no values beside it. So these are actually my stems, okay. This is the most left part of my number, which is the tens, and these are the leaves. All of these are my leaves. Putting the stem beside the leaf means that the first observation here is 39, and here 43, and here 53, 55, 57, and we do have 9 and 9 as leaves on the stem, which is labeled by 5, so 59 and 59. Sorry. And 6 also, I have 1, 2, 3, 4, 5, 6 leaves, so 6 numbers we're having the stem 6. And lastly, the last stem, which is 7, I do have 2 leaves, 72 and 76. And as you see, I could read from the stem and leaf plot the actual number. I have the stems, each value here is having unit 10. So this is 30, 40, 50, 60, 70. If I have here something like 11, so it means it's 110. 110. So these are measured in tenths unit. And as I say, and as you see, I could read from the stem and leaf the original raw data. So I know already from the look on that stem and leaf plot that this is my data set. So I keep track of the data values themselves, and this is the actual data, or sometimes we call it raw data. And here I can see that at the beginning, small data, small frequencies, and then here between 5 and 6 I have the main bulk of my data, and then again small. So I can see here is that I do have that shape. Okay, so smaller values toward smaller units, 30 and 40, and many values between 5 and 6. So I could say it's a little bit skewed to small values, which is, if this was the x-axis, left value, because 3 and 4 are smaller than the other one. So this one is skewed to left. And if I had outliers in my data, it would appear here. Suppose with me I had a value which was 10. So 10 would appear, if I had here a value of 10, I would have here seen a stem of a value 1, and beside it is a value, say I had 11, so 1 and 1, which is 11, okay? And in between 2, stem 2 has to be represented, so I have 1, 1, and 2 has to be represented with no value, so I'm not gonna put any leaf here, so an empty line just with a stem. So I do have continuity in my stems, like 1, 2, 3, and so on, and I could look at the 11 value, the hypothetical value, which is 11, which is up here. This one will be my outlier if I had such case. Let me graph it together using this example. We do have exam scores on a statistics exam, and we would like to organize it or represent it using stem and leaf. So these are my dots or my points. To do it on stem and leaf, all what I need to do is to know what are the values of my stems. Here I do have only tenths and units, so the value of the stem is of value 10. So let we see what is the highest stem I do have. It's 90. The smallest one is 40. So it's a good idea to go ahead and actually arrange these in ascending order. So let we arrange it. This is 49, the smallest, till the highest one, 98. So I can say, okay, since I do have just my numbers of tens, like tens digit and the units, so my stems are gonna go from 40 till 90, and I'm gonna put the leaves. So my stems, unit of my stem is 10, and the unit of the leaf is 1, and these are my stems going from 4 to 9. Even if I had here a stem with no number here, I have to put it because it's in the center of my stems, which has to go continuously from 4 to 9. So 4 to 9, and I'm gonna just put my leaves now. 49, so the first leaf is of value 9, then I'm gonna head to second leaf with my second stem, which is 6, and then 8, and so on. So this is my completed stem and leaf. Again, I do have here something that we were gonna call it later by model class, by model distribution, because I do have here 2 peaks. Okay, I could talk about that, but later we will see it in details. Now, histogram is my third graph that is suitable for quantitative data, and specifically grouped quantitative data. So histogram is for grouped quantitative data, and it is for large or small data set. And it will look like a bars. However, these bars are stick together, so no space between any two bars. It has to be stick together, and it is only vertical bars. And again, as I said, it is based on grouped frequency distribution, so continuous variables. And the histogram could be graphed using frequency or relative frequency, where your x-axis will have the class boundaries, while the y-axis will represent either the frequency or the relative frequency as you desire. What are the class boundaries? These are the beginning of your class. So 20 is a class boundary, the lower class boundaries. 30 is the lower class boundary for my second class, and so on. 40 is for the third one, and 50 is the fifth one. So x-axis will have all of these, while the y-axis, if you decided to use frequency, will be measured using these frequencies. So the height of each bar is gonna be represented as its suitable frequency for each class. And I can read the shape very easily from a histogram, and also, by the way, I can read the outliers. Okay. Ogive. Before we see a histogram, let me talk very quickly about the ogive. Ogive is also a graph that could be used for continuous variables in a grouped frequency distribution. So, and what we are gonna use here, you are gonna use the upper boundary of your class on your x-axis and what is known by the cumulative frequency on your y-axis. So upper class boundaries, so the higher class boundary would be on your x-axis, which is the horizontal axis, and cumulative frequencies on your y-axis. But what is a cumulative frequency? For cumulative frequency is just how many frequencies are less than the upper boundary of this class. So another word, how many frequencies did appear in any previous class lower than the one I am taking its upper boundary with me. So let me see an example. It will be easier to talk about it from an example. Suppose we had that table for 65 items, and these were invoice, 65 invoice, and we are measuring the payment time for those 65 invoice. And the classes happen to be from 10 to less than 13, and then from 13, from 16, and so on till 28 and less than 38. Upper boundaries would be those, these are the lower boundaries, and the highest one would be the upper boundary. For the ogive, we are gonna say, okay, less than 13, so I'm gonna just put it at 13. So if these are my frequencies, so I'm gonna ask myself for the first one, how many frequencies did appear to be less than 13? How many frequencies among these 65? Only 3. How many were less than 16? Those 3 plus those 14. How many were less than the upper boundary of that third class, which is less than 19? So how many were less than 19? Those 24 and those previously 17, which are these ones. So all of these were less than 19, and so on. Till you will find yourself at the last class, how many were less than 31? These are the total sample size. So the last class has to end with 65, and the first class has to begin with the first frequency. And to very optimal in terms of graphing. We would like to begin that ogive at the 0 point. Usually we say how many are less than 10. None of these 65 were less than 10, so you will say, okay, the first cumulative frequency would be 0, and we will see that on the graph right now. So if I would like go back to talk about the histogram, how to graph it. Again, for each class, I am gonna just represent it by a bar. So the class from 10 to less than 13, it will have a bar which is equal in height to 3. And the second class will have a bar which is equal in height to 14 if I'm using frequency on my y-axis. So these bars are stick together, and this is a nice histogram. As you see down there, 10 till 13, I'm using that beginning or the boundaries of each class. So each class is gonna begin at its lower bound and end at the next lower bound for the next class. This is a histogram, and as you see, the main bulk of the data is here, and it's like they are rising up and then going down again, tailing till very small. So it's like you are going down with a long tail, and because of that we will call that distribution, it's skewed to high values, and high values on my x-axis is to the right, so it's skewed to right. So the main bulk is to the left and its tail is to the right, so we call it skewed to right. Now to talk about the ogive, again we are gonna use the high boundaries, which are here 13, 16 and so on till 31, and the cumulative frequency. So your x-axis will have the higher or the upper boundaries, which is for that one 13, 16 till 31, and at the 13 I'm gonna graph not the 14, I'm gonna graph the cumulative frequency. So this is my 13 and the cumulative frequency is at 3. This is at the height of 3 according to our graph. And at 16 I have a height of 17, and so until the last one 31 I would have the point at a height of 65. Now let me go back here. I did begin, let me talk about that first. I did begin at upper boundary 10, but I don't have an upper boundary 10 because I didn't have any class before 10. But it's okay, I'm gonna just begin at 10 and I'm gonna give it a cumulative frequency of 0 because none of my 65 were less than 10. So I can begin my graph nice and decent from 0 till the highest point, which is 65. And as you see, it's always increasing. You will never find it like going down and up again because I am adding, I am subsequently adding. So adding, always increasing. Now what is the idea of these purple lines? From that graph you can read many information. Like what? You could ask yourself, okay, 30 invoice in my data here are having time less than what? So 30 invoices are having time less than that value that I can read from here. Maybe this is 18. So 30 invoices are having payment time less than 13. I believe it was 13 days. The units of this payment, I believe it was days. So I can read such information from that graph. Like if you were interested to know what is the time that 50 invoices were having a time less than it, it's like go from 50 invoices till you hit your curve, go down and read it from here. Okay. And our last graph would be the time series graph that we're gonna discuss today, because we had a box and plot graph in that list for quantitative variables, but as I said, it's not to be discussed today, maybe in a coming lecture, not in today's lecture. So our last graph here is a time series graph. Here you will have data for a specific variable phenomenon that is over time. So your x-axis will be always representing time, months, days, whatever, years or whatever. Your phenomenon is represented on your y-axis, and your target is to see whether you do have a pattern of trend or not in your data, and also to detect any seasonal effect or repeated pattern that occur over time. So for this graph here, temperature over 9-hour period, at 12 o'clock the temperature was around 41, I would say, and 1 o'clock it is roughly 44, and you are gonna just represent your data according to the time it appeared. And the trend, do I have a trend? Well, it's not an increasing trend in general or decreasing. However, it's increasing till 5 o'clock, and then it began to decrease again. So not in general overall increasing trend or overall decreasing. It's at the beginning increasing and then decreasing. How about the cycling effect? Well, I didn't have here any cycling effect that is repeating, so I didn't have something like down and up and then down and up. So it's here no cycling effect during that period. Maybe if we extended our time here for more than 9 hours, we could have seen that cyclic effect. And as a example for that, in that graph, you see this is like that pattern is repeating itself over time. But this is a different example than that one. This is just to let you see what do I mean by the seasonal variation. Okay. So now, before ending our lecture, we would like to talk about distribution shapes. Maybe in my previous slides, I did talk about skewed to left and skewed to right, and here it's the shape of the distribution. If you had a histogram like that one, like nice and clean like that one, the highest bar is in the middle and symmetrically going down in that direction and that direction exactly the same, we are gonna call it bell-shaped distribution because it's like a shape which is upside down like you see here. Sometimes also we call it single peak because it has only one height, one model class here, one peak. And not only single peak and symmetric, to emphasize that it is having an asymmetric pattern on its both sides from the model class or from the single peak. So single peak and symmetric, this means bell-shaped. Sometimes you will, and this is by the way the nice shape that you hope that all of your distributions are taking, at least in statistics. Excuse me. The second shape is you could end up with a shape which is looking like that one. We call it a uniform shape for the distribution. And also sometimes we call it flat or rectangle. This is like saying all of the heights for all of my parts are having roughly the same height. In this case, we are calling it a uniform distribution. Okay. Right skewed, and this is like the graph we have seen before in one of our examples. You remember when I said the main bulk is here and the left parts are higher than the high in terms of the frequency, so most of your frequencies are here, and then it's gonna go down with the tail like that. And I said it's skewed to right, the distribution or your histogram is skewed to right. This is the pattern for skewed to right distributions. Okay, the tail is to the right of your x-axis, higher values here, small value here. I could also call it positively skewed, just because the higher value are here, so positive is skewed to positive values, okay, and the negative values are there. And this is to the opposite of another shape, which could be the opposite of that one. Your tail is to the left, so towards the negative values of your x axis, so we call it negative skewed. Lastly, we do have what is known by the bimodal class, and I did talk about bimodal distribution, and we did talk about it in our one of our graphs. It was the stem and leaf graph when I said I do have two peaks in it. So if you do have in your histogram, or by the way, you could have the same shape with a curve, because sometimes we represent it like a curve like that, so it would be go up and down and then up again and down. This is a curve which is similar to the behavior we see here on our histogram. Two peaks of the same size exactly, or roughly the same size, we will call it bimodal distribution. If these two peaks were exactly at the end of your histogram and at the beginning of your histogram, looking something like that, we will call it a U-shaped distribution. So our last point that I would like to emphasize here is misuses of statistics. When you are gonna read a report or an article, or just reading statistics from a magazine or whatever, just read and think about it. Suspect always the sample. So do you have these statistics from small samples? Are the sample size reasonable or not? And we did see that in our case too, where we talked about 90% of students do like statistics versus 10%, and we ended up with knowing that the sample size was 10. Another issue is to think about the average. Whenever you read an average in any magazine, any report, or any statistic you came around it or across it, think about whether that average is really a mean or it's just a mode or a median, okay? Because in some cases, these mean, median, and mode, in some cases, they could differ from each other, like dramatically. And some could use that issue and use one of these measures, the one which will make the result look better, use it rather than the other one which should have been used. So just make sure when you read averages, what does that average mean? Is it median, mode, or mean, or even mid-range? So you need to check it. Another misuses in statistics, sometimes you will end up with a percentage that is reported just to emphasize something and say it's really very good percentage, very high percentage, like the satisfaction level was, for example, 80%, and then you will end up with knowing that, well, it was a small sample size and that 80% is nothing than just maybe 8 out of 10, so you need a larger sample size. So sometimes people are changing, or some people are changing the subject, reporting percentages if this is for their good or to make the result look better. And some other time you could just read the percentage, which is like maybe very small, 3% decrease in the satisfaction level, and that 3% could be in real numbers, like maybe 6,000. So 6,000 out of something. So I mean, sometimes let me give you another example here. If you hear something like someone is saying, well, the expenditures increased just 3%, okay, during my administration. Okay, some politician is saying that, and that 3%, if you looked at the real number, could be as a number like what, like 60,000 or something. So you need to make sure, is it better to talk about percentages in that case or real number? So just ask yourself that one question before deciding to go with results that are published. And lastly, detached statistics. You might read in some article something or a statement like saying, well, our brand of cereal or whatever has 1/3 fewer calories. So it's like, okay, fewer than what is the reference point here? So sometimes you will find a statement talking about a comparison without mentioning what is the reference here. So this is some sources of misuses in statistics. And lastly, misleading graphs. You could look at a graph which is really not represented correctly, and we did discuss these graphs or see some of these in our case 2 last Friday and Sunday. We did see some cases like that. So bottom line is just you need, when you look at any statistics, to ask yourself these or think about these issues. Maybe I did also forget to talk about faulty survey questions. When you are analyzing or reading a report from specific survey, ask yourself whether this analysis are coming from good phrase questions or not. Is there any tricky wording in the question itself, so that the answer to those questions are really not representing the real scenario? So you need to think about, at least give it a thought, okay? Go back to the questionnaire and read it, okay, before admitting or taking the reported result. And this is the end of our lecture. Next lecture would be about central tendency measure, but before that we will see case 3 and solve it first, and then take the theoretical part of it next Wednesday. So see you next Wednesday. So again, it's a table summarizes the number of